In the previous chapter, I described the alcohol functional group as arising from water swapping out a hydrogen for an alkyl group. Okay, and that's where we get the OH of our alcohol. In this chapter, we're going to continue on in that pattern. When we look at ethers, we basically taking a water molecule and swapping out both hydrogens for alkyl groups. So we have a carbon-oxygen-carbon bond. And that's kind of the hallmark of an ether. Epoxides are very similar too. You have a carbon-oxygen-carbon bond, but those two carbons are connected to each other as well, making a three-membered ring. If we take our oxygen and swap it out for a sulfur, okay, so instead of using water, we're using hydrogen sulfide, and we start swapping out hydrogens for alkyl groups. Then we get to thiols and sulfides. Thiols are essentially alcohols but with a sulfur instead of oxygen, and sulfides are essentially ethers with a sulfur instead of oxygen. So here, let's start with each of these functional groups in turn. Let's start with an ether here. And so you can see here that we have our two R groups, our two alkyl groups, attached to our oxygen. Okay, so you can see that the oxygen, the structure around that oxygen is bent, just like in a water molecule. Okay. So the one thing to watch out for here is you've got to be careful that the R groups are just alkyl groups. If there are other things on them like carbonyls, then you might not be looking at an ether per se. Okay, so for example, down here, you don't have you have a carbonyl on the group to the right. So what you're actually seeing here is an ester, not an ether. Okay, we'll talk more about esters next semester, but oh, that rhymed. But anyway, we'll get into that later. That's actually a carboxylic acid derivative, and we'll spend a whole chapter talking about those. Okay, but my point here is that you can consider this an ether, even though there's a carbon-oxygen-carbon bond. This carbonyl next to that makes this a carboxyl functional group, and rather an ether functional group to be more specific. Oh, sorry, an ester, not an ether. Okay, so that being said, ethers are pretty common. You'll see them in lots of places. Let's talk about nomenclature for these. So when you probably have come across ethers that use just the common names. Now, because an ether always has two alkyl groups attached to your oxygen, the common naming system is relatively straightforward. You just name each alkyl group alphabetically and end with the word ether. So for example, if you have an ethyl group and a methyl group, well, you start off with the ethyl group that starts with an E, so it's ethyl methyl ether. Okay, here we have a tert-butyl group and a methyl group. We alphabetize that with a B for butyl, not with tert, so it's tert-butyl methyl ether. Okay, now, please note, these are common names. These are not IUPAC names, okay? So let's get into the IUPAC names. Oh, before I move on to the IUPAC names, quick note here about probably the most common ether you come across. In fact, it's what people think of when they hear ether. Diethyl ether is well, again, it's the most common ether you're probably going to see. It's used as a solvent pretty commonly. You can, if you have two of the same alkyl group, as you do in the case of diethyl ether, you can just put the prefix di before that. Okay, so you don't have to say ethyl ether or something. That would be weird. All right, so let's talk about the IUPAC system. Now, with the IUPAC system, we take our larger R group, our larger alkyl group, and that becomes our parent chain. And you've seen that trend in all of our other compounds that we've looked at in this semester. What we're going to do with the smaller alkyl group is we'll consider the oxygen attached to it, and we treat that substituent as an alkoxy group. Okay, so it's just an alkyl group with an oxygen attached. Okay, so you're going to use the prefix for that substituent by going off the number of carbons, and then just add the suffix oxy to that. So here our parent chain has 5 carbons, so that root word is pentane. And for our substituent, we have 2 carbons coming off of our oxygen, so that's an ethoxy pentane. So with that in mind, let's try naming this molecule. And when you're done with that, you can try drawing this molecule out. Again, I would recommend starting off with the parent chain and then treat the alkoxy group as a substituent branching off that parent chain. Okay, so feel free to pause this video and try that out. Okay, so if you're back, hopefully you should have gotten these as your answers. All right, so the key things here is our larger group here is going to be our parent chain. Okay, so we've got 1, 2, 3, 4 carbons. Okay, so that would be a bute prefix to that parent chain. It would be butane, but there's a double bond in there, so it's actually butene. Our double bonds between carbons 2 and 3 of our butane, of our 4 carbon chain, so it's 2-butene. We have methyl groups at a methyl group at the 2 position and a chlorine at the 3 position. So we mentioned that in the name here. But don't forget, we treat this alkoxy group as a substituent as well. So we've got 2 carbons in that alkoxy group, so it becomes ethoxy. And in our butene, this is going to be our number 1 carbon, right? We want to start numbering it closer to the side of the double bond, but since the double bond's right in the middle, it makes sense to have this be our number 1 carbon here. So it's 1-ethoxy. Since E comes after C, well, we put it in that order as well, and methyl comes after that. So you list all your substituents in alphabetical order. So it's 3-chloro, 1-ethoxy, 2-methyl, 2-butene. Okay. Of course, you have to talk about you have to mention any stereochemistry. In this case, since we have an alkene, we can use a cis or trans designation. So we have 2 methyl groups here, and they are trans to each other. So here they use the EZ nomenclature, but we could have used trans to describe this as well. Okay. That being said, if we want to assign priorities to things, the chlorine has a higher priority compared to this methyl group, and out of these 2 carbons, this carbon has an oxygen connected to it, so that gives it a higher priority compared to this one, which has only hydrogens. And so the 2 high priority groups are away from each other, they're across from each other, so that's the E designation that they've used here. Okay, though again, like I said, trans would probably have been just as appropriate here, probably more appropriate. For the second question, there actually seems to be a bit of a mistake, I think, on the publisher's part here. This actually doesn't match up with IUPAC nomenclature properly. It looks like they've given priority to the alkene part of cyclohexene 3-ol. Really, that alcohol group, since it's terminal here, it's what's defining that name. That should automatically be in the 1 position. So take this question with a pinch of salt. They've used what seems to be, this might be a common name, but it isn't a proper IUPAC name. Okay, so going off this incorrect name, though, it looks like they've got a cyclohexene. It looks like they've, by not putting a loc in there, it looks like you're supposed to assume that that alkene is at the number 1 position, and the alcohol is at the number 3 position. Okay, so going off of that, it looks like they've put the double bond here between carbons 1 and 2, and your alcohol group's at the number 3 position there. Okay, our methoxy group, of course, is at the number 1 position as well, and that's a methoxy group because there's a methyl attached to that oxygen. All right, and then the question tells you that you've got this chiral center over here, which is the only chiral center in the molecule, has the R designation. So that tells you whether to use a solid or a dashed wedge for the alcohol group. Okay, let's talk a bit about the properties of our ethers. With the bond angle that we see in our ethers, let's compare that to water and to an alcohol, and ask ourselves, why is that bond angle a little bit different? It comes down to the bulkiness of the groups around your oxygen. The lone pairs, of course, are the same, but notice that in water we have 2 hydrogen atoms, which of course are very small. In the case of an alcohol group, that alkyl group takes up more space than a hydrogen, and that's why that bond angle gets a little bit bigger due to the electrostatic repulsion of the clouds of electrons around those atoms. And then, of course, when it comes to ethers, where you've got 2 alkyl groups, you're going to have even more repulsion. Those groups are even bulkier than just hydrogens. Okay. But yeah, you're generally going to be in that 109-degree bond angle ballpark that you typically see for tetrahedral, Vesper geometry, right? For that, it's tetrahedral in terms of electron pairs. So if we were counting our lone pairs and counting the repulsion from those, it's a tetrahedral shape. Okay, and so that bond angle is somewhere around like 109, 109.5 if you had a pure tetrahedron, right? But of course, since your lone pairs repel each other more than atoms do, that bond angle in water is only 105 degrees instead of 109.5, like it would be in something like, let's say, methane, where you've got, equal bonds coming off your tetrahedral center. Okay. Yeah, so just something to keep in mind in case you're wondering why that bond angle is not exactly the same for an ether compared to an alcohol, compared to water. All right, more importantly, though, we want to consider what types of interactions will ether molecules have with each other and with other molecules that are mixed in with them. Okay, because this affects properties like your boiling point. It affects properties like solubility, and so we want to think about this. With alcohols, this was a pretty major interaction to consider because alcohols, like water, are capable of hydrogen bonding. You have an oxygen that's directly connected to a hydrogen, and those are the requirements you need to meet for hydrogen bonding. So the question then to ask yourself, is an ether capable of hydrogen bonding? Well, if you had a sample of the pure ether, the answer is no. There's no hydrogen connected to your oxygen. It's a polar molecule because that molecule shape is bent. Those lone pairs on that oxygen are not the same as those alkyl groups, thereby bending the molecule, thereby giving you a partially negative half of the molecule where the oxygen is. Okay, but you do not have hydrogen bonding, which is a much stronger interaction than dipole-dipole interactions. Okay, so that's something you'll notice with the boiling point of ether compared to, let's say, an alcohol or water. Okay, now that being said, can ethers interact through hydrogen bonding with other molecules capable of hydrogen bonding? And the answer is yes, right? So with a small enough ether, you can still have have a protic solute or solvent, for that matter, like an alcohol, share its hydrogen or have its hydrogen interact with the electronegative oxygen on your ether. Okay, so that is why ethers can dissolve. They're polar. They're very polar they're polar molecules, but not as polar as your typical water molecule or alcohol. Okay. So that's something to keep in mind with the boiling point of an ether compared to that of an alcohol or water. So we can see that here. Look at your boiling points. Notice that if we compare ethanol, which is an alcohol, to dimethyl ether, which is an ether, of course, and propane, which is an alkane. Okay, your alcohol has a significantly higher boiling point, and of course it does. It has hydrogen bonding, right? If you have a sample of just ethanol, if you have a sample of just your ether, again, you have only dipole-dipole interactions. There's no hydrogen bonding, so that is why there's a significant drop in boiling point. Now, that being said, dipole-dipole interactions are still more than London dispersion forces, so that's still also a much higher boiling point than that for propane. Now, let's compare ethers themselves. If we have multiple ethers, they're all polar, right? How does the alkyl group affect our intermolecular forces? Well, as you increase the size of your alkyl groups, they start overcoming the polar part of the molecule. You start having more of a nonpolar London dispersion force interaction. But remember, that's dependent on your the amount of electron density you have to push around. right? Well, the bigger your ether starts getting, the more electron density you have to play with, and your boiling point starts going up just because of increased London dispersion forces. And that's what we see in this trend here. Okay, so even though we are increasing the nonpolar regions, the fact that we can increase the level of London dispersion forces is why a larger ether has a higher boiling point than a smaller ether. Okay, so that being said, we can use this to our advantage. Ethers have relatively low boiling points, and they are fairly polar, right? Which means that we can use them to act as solvents in a lot of reactions, and then we can evaporate them very easily to leave behind just our product. Okay, they are aprotic, right? We saw that they can't do hydrogen bonding, but again, that's a good thing when we need an aprotic solvent. Okay, as we saw back in our chapter on substitution reactions. All right, you may recall that when we wrote out the reagents for a Grignard reagent, okay, for producing a Grignard reagent, we would take our alkyl halide and reflux it with magnesium, but we would do it using ether as our solvent. The reason for this is those electronegative oxygens help stabilize the positively charged magnesium ions. Okay, so that's again, it just helps keep your Grignard a little bit stable and leave it available to react with what you want it to react with. So to that end, crown ethers are a class of ethers where you have a ring compound and you alternate groups of carbons with oxygen. So you've got multiple ether groups held together in this large ring. Okay. Regarding naming them, you can see that they are named by taking the total number of atoms, oxygens, and carbons in your ring, forming your ring. So when I say total number of atoms, I'm excluding the hydrogens. I'm talking about things that specifically form the ring itself. Okay, not the things branching off of it. So we've got 12 carbons and oxygens forming this ring, so that number goes in front, and out of those 4 are oxygens. That's the number that goes at the end. Okay, so that's how we get different types of crown ethers here. Now, the cool thing with crown ethers is because you've got all of these oxygens here, sort of pointing towards this space in the middle, this cavity, you can coordinate something, typically a metal ion, in the middle here. Okay, so crown ethers are great for stabilizing a metal center and getting it ready to do stuff. Sometimes it's great for just transporting it through various media, but oftentimes it's great for setting it up for a particular reaction. Okay, so here's a picture of that. So if you have an 18 crown 6, we can see here a potassium ion fits like just perfectly into that space. Okay. So yeah, so it kind of helps stabilize your cation and keep it away from any other anions, which then leaves your anion free to react. Okay, so here's a picture of what that looks like. So if we combine this crown ether with potassium fluoride. Now, remember, fluoride's pretty reactive. It's pretty electronegative. It really wants that potassium ion to connect to it. So by introducing this crown ether, which also really wants that potassium, it's possible to keep that potassium ion away from your fluoride, and now your fluoride ion is available to react with things. Okay, whereas typically if you just had potassium fluoride in there by itself, your fluoride might not be free to react. It might stick to the potassium ions around it instead. Okay, so that helps with solubility too. So instead of having potassium fluoride precipitate out, your crown ether helps free up that fluoride to dissolve in your benzene and allow it to take part in this reaction. So we can see here that fluoride can actually act as a pretty decent nucleophile in this reaction. But without that crown ether, this reaction wouldn't go forward. Okay, so we can change the size of the crown that we use depending on the size of the cation we want to bind up. Okay, so you can see that going, as we go down group 1, our ions get bigger as we add more and more shells of electrons. So you can see that the smaller lithium ion, we would use a much smaller crown, like 12 crown 4, as opposed to that 18 crown 6 we use with potassium. Okay, so let's start looking at some reactions of ethers. Let's start off with reactions that make ethers. All right. So to do this, we can typically do a dehydration reaction of ethanol. So we can basically have an ethanol molecule react with itself. So have one ethanol molecule react with another ethanol molecule, and that will cause that will create your ether as a byproduct, or as the regular product. Okay, now this is actually how we make diethyl ether. This is that common ether solvent that we typically use. All right, so how does this work? Well, we start off with our with an ethanol, and you can protonate it to make it more prone to a nucleophilic attack. Because remember, having that protonated alcohol group makes it a really good leaving group as water. So now this is a good leaving group, which means that we have another ethanol molecule come in and act as the nucleophile, and so it attacks that alpha carbon, kicks off this leaving group, and now we have this oxygen carbon bond of our ether. We have this second ethyl group attached to our oxygen. Okay. Now this, of course, will have the oxygen protonated, so you need to deprotonate that to get rid of the hydrogen and give you the neutral molecule, the neutral product. That's what happens here. So here's our product once that nucleophilic attack has happened. So we have just a proton transfer occur, and that gives us our final diethyl ether product. All right. So regarding so a quick note here about so with diethyl ether, this is pretty straightforward because you only use ethanol and acid, right? You've got the same alkyl group on both sides of your oxygen in your ether, so we can use just ethanol, right? Just something with that ethyl group. This gets a little trickier if you're trying to do this with an asymmetrical ether, if you have different alkyl groups, because if you use this method, you get a mixture of products, and not all of it is the product you want, right? Maybe just only half the product you get is the ether that has both alkyl groups. A quarter of your product will probably be each dialkyl product. So let's say we use methanol and ethanol, and you want methoxyethane as your product. Well, half your product will be methoxyethane, a quarter of your product will be dimethyl ether, and the other quarter of product will be diethyl ether. Okay, so you can't control that with this method. So how can we control things? All right. So to do that, we're going to use the Williamson ether synthesis, okay, as a way to kind of force our ether to go down one direction. Right. We kind of add things on one step at a time. So in the first step, we're going to take our alcohol, one alcohol, and we're going to convert it into an alkoxy base. So to do that, we use sodium hydride. The hydride ion plucks off a proton. So hydride itself can be basic. It plucks off a proton and leaves as hydrogen gas, right? And so we wind up making the sodium alkoxide salt as the product. Alkoxide's a base. So it's a base, but also a good nucleophile. So as a nucleophile, we can then introduce an alkyl halide of some sort and have it attack that alkyl group. Of course, our halogen's a great leaving group, leaves as a halide. And now we've added our second alkyl group to our oxygen, and here's the ether we want. Okay, and again, notice that we have two different R groups. Okay, I'm guessing this R here is not, as long as you didn't use methanol here, you're going to have two different R groups. Okay, so something to keep in mind about how we tackle this problem. Now, we have issues here as well, of course, right? I mentioned that in addition to being a nucleophile, your alkoxide is a base, and it's a strong base at that. So you want to watch out for alkyl halides that are secondary or tertiary, because here we're doing an SN2 mechanism, right? We have this nucleophile directly attacking this alkyl halide and kicking off that halide. But what if you had a secondary or tertiary substrate, especially a tertiary substrate that doesn't like SN2 mechanisms? Well, instead what might happen is that your alkoxide here acts as a base and deprotonates that and actually does the elimination reaction. Okay, so watch out for that. Okay, be careful of what you want your ether to look like. Okay, so so here we've added on a methyl group, and so that's no problem. But if this group was a secondary or tertiary alkyl group, then you might want to think, okay, is this necessarily the pathway I want to use to make this product? Okay, so let's have a look at where we've run into that problem. So here we want to make an ether that has a tert-butyl group and a methyl group, and that's where we've got that issue, right? So you've got to be careful about which step you start off with. Which alcohol do you start off with? Notice that we have to start off with tert-butanol as our alcohol that we convert into an alkoxide. Okay, and then we have that react with methyl iodide to make the final product. If we tried doing that the other way around, this would not work, right? If we use methanol to make sodium methoxide as our nucleophile, would that nucleophile attack this tert-butyl iodide to make the product? And the answer is no, right? This is not a good site for an SN2 mechanism. So instead, your methoxide would eliminate, it would pluck off a proton from one of these outside carbons, and it would form a double bond between these two carbons, okay, and kick off that this iodide then. So you'd wind up making 2-methyl-1-propene as your product instead. So with that in mind, let's try a practice problem involving that. So here's an ether we want to make, and the question asks us to use the Williamson ether approach since it's asymmetrical. Now, they've used some stereochemistry here. They've used a dashed wedge to get you to think about which one was your alcohol, which one was your alkyl halide. Like, where did your two alkyl groups come from? Okay, so note that the oxygen is connected to the cyclohexane through this dashed wedge. All right, so I'll point that out and I'll let you think about that. Please note that in real life you probably don't have to worry too much about that dashed wedge, just because this carbon's not a chiral carbon, right? This is a symmetrical molecule. So whether this is a solid or dashed wedge actually isn't really important. But I think they include that here so you could think about which way you want to do this reaction. All right, so feel free to pause this and take a stab at this. All right, so if you're back, you'll notice that I drew your attention to that to the stereochemistry of this, and the reason for this is that tells you that this ethoxy group was your nucleophile, okay, as opposed to being the other way around and having a cyclohexoxy group as the nucleophile on an ethyl halide. All right, because we could have done that either way. To be honest with you, I'd probably do it the other way around. I would have the ethyl halide be my, I would use that as my halide in the second part of the process, just because it'd be a primary alkyl halide. With the secondary alkyl halide, it's still going to probably encourage SN2, but you never know. You might get some elimination reaction, and that'll decrease your yield. So personally, I wouldn't do it that way. But based on what they're showing us here, I'm guessing they're trying to get you to see that this was your nucleophile. All right, so how would we set this up? So we would start off with our ethanol as our alcohol, right? and we'd react that with sodium hydride. Okay, our hydride would basically pluck off this proton, get it to leave as hydrogen gas. All right, and we'd be left with sodium ethoxide, right? And of course, sodium here is just a spectator ion, right? We're just going to not really care about that. Really, it's this ethoxide that's going to act as our nucleophile. Here, let's put lone pairs on this so it's a little bit easier to see what's going on here. So lone pairs there. Okay, so we bring in our cyclohexyl. I don't know. Let's make this an iodide. So cyclohexyl iodide. Okay, I'm going to use a solid wedge here just to show you where that dash wedge is coming from. So that is going to do an SN2 backside attack. It's going to attack from behind this carbon and kick off this iodide. But because it's attacking from the opposite side, that's why we have this dashed wedge over here. Okay, so oops. Okay, so you're going to lose an iodide ion. Lose that ion, and you get the product here accordingly. So another way to synthesize an ether is to actually look at a way we synthesized alcohols back in our chapter on addition reactions to alkenes. So if you recall, with oxymercuration, demercuration, we can do a Markovnikov addition across our alkene, and we basically use mercury acetate and water in the first step, and then subsequently use sodium borohydride, right, to get rid of the mercury. But the bottom line is that we're adding a water molecule across that double bond. Our OH from our water molecule goes to the more substituted carbon, following Markovnikov's rule, and the hydrogen goes to the less substituted carbon. Okay. However, instead of using a water molecule, if we used an alcohol, instead of getting an OH group here, we would have an alkoxy group. And if we have an alkoxy group on here attached to our parent chain, well, this is an ether, and that's one way to make an ether. It's just doing the same mercuration demercuration, but instead of using a oxymercuration, we're going to use a alkoxy mercuration. Okay, so that's the difference. Okay. In terms of regiochemistry and stereochemistry, the mechanism's still the same. So we're still doing a Markovnikov addition. Your alkoxy group is still on your more substituted carbon. In terms of where that alkoxy group goes, well, in the mercuration step, remember that's it's going to be an anti-addition because the mercury center takes one side of the alkene, and so the alkoxy group would add to the other side. However, the sodium borohydride step, the demercuration step, it is not stereoselective. So you actually get a mixture of syn and anti products there. So that hydrogen isn't necessarily cis or trans to your alkoxy group. Okay, so those are ways we can make ethers. Let's look at reactions we can use ethers for. All right, so what can we use ethers to do? So because ethers are aprotic, this kind of hinders their ability to do certain reactions, right? We can't make their resulting products more stable. Even if that oxygen were nucleophilic, we can't make the product stable by doing a simple proton transfer like we do with an alcohol, for example. All right, and your alkyl groups are horrible leaving groups. Okay, so that can be an issue. All right, you might be able to do some substitution reactions with an alkoxy group as a leaving group, but that's something to consider there. Okay, so when we look at an ether, right? So let's use this one as an example here. Okay, so there's our oxygen, of course, very electronegative, and I mentioned that that could be kind of nucleophilic, but we're going to run into issues with 3 bonds to that oxygen. and you can't really break these oxygen-carbon bonds very easily. So that kind of rules out an ether acting as a nucleophile. So what else could we do? Well, I mentioned that you can have an alkoxy group be your leaving group. So really, it's the alpha carbon connected to that oxygen that's probably the more reactive site. Okay, so ethers aren't bad candidates for acting as electrophiles, and so you can have a nucleophilic attack occurring at that electrophilic site, at that alpha carbon. All right, so let's see this in action here. So we can actually cause ethers to get cleaved around that oxygen. In other words, we can add the alkyl groups accordingly to a halogen, if we use a halide ion as our nucleophile. Okay, so how does this work? So you start off by protonating your ether, that oxygen in your ether. So this is going to make your leaving group an even better leaving group. Instead of leaving it as an alkoxide, it's going to leave as a neutral alcohol. But one of your alkyl groups then is, as I mentioned, a prone site for it's a great electrophile, so it's a prone site for a nucleophilic attack. So we see that the halide from our acid is the nucleophile that attacks that alpha carbon and kicks off your leaving group. Okay, it kicks it off as an alcohol. And so here's our first equivalent of our alkyl halide. Now, with the resulting alcohol, of course, you can do the same process all over again. Protonate that oxygen. Now you've turned this into a great leaving group as what will be a water molecule. Have your nucleophile come in again, attack that alpha carbon, kick off your water leaving group, and here you have a second equivalent of an alkyl halide. All right, so in both cases, you've kicked off the alkyl groups in the form of alkyl halides using an SN2 mechanism. Okay, so let's try an example out here. So here we have a generic ether where we have a benzene ring as one group. It's an aryl group, not an alkyl group. But here we have we have just a generic R group. Okay, that's our alkyl group. Let's look at the products we're going to get if we try to do the same mechanism. Okay, thing to watch out for. Remember, we've got a benzene here, not an alkyl group. So is this carbon going to be suitable for a nucleophilic substitution? No, we've seen that benzene does not handle a simple nucleophilic attack very well. All right, so we'll spend like I said, next semester we'll go into more detail on how aromatic compounds like benzene work. We'll look at electrophilic aromatic substitution reactions, but simple nucleophilic substitution won't work here. All right, so basically it'll be a similar mechanism as we saw before, but the key thing here is we're going to have this R group is the one that's going to get attacked with that halide. So you first have the proton from your acid protonate that oxygen to make a phenol leaving group. You have your halide ion do a nucleophilic attack onto the carbon of this alkyl group, and that'll cause this bond to break. These electrons will go towards the oxygen, and you'll have phenol be your leaving group. Okay, now in terms of trying to do these types of cleavage reactions, typically you want to use hydroiodic acid or hydrobromic acid. Hydrochloric acid and hydrofluoric acid aren't going to be as effective. Okay, hydrofluoric acid even less so than hydrochloric. Right. So keep that in mind in terms of, I think it basically has to do with their nucleophilicity. With your iodide and bromide ions, those are large and squishy with their electron density, which helps them carry out this reaction. Okay, so let's try another mechanism with this one. So this is actually, so again, it's going to be a similar mechanism to what we saw, a few slides back. The only difference is instead of methyl groups, we're going to make a cyclohexyl bromide, and we're going to have ethyl bromide as our two byproducts, and of course water at the end. So here's the full mechanism. Okay, so we of course protonate our oxygen first, Then we have our bromide come in. It looks like we're going to lose our ethyl group first, which makes sense. It's a primary alkyl group, so more prone to an SN2 mechanism. It's less bulky than this one. So you have that bromide come in, kick off your cyclohexanol byproduct. Of course, then you can go on to protonate that oxygen, and then have your bromide nucleophile attack that carbon, kick off this water-leaving group, and you now have your ethyl bromide, or cyclohexyl bromide, as the other product. Okay. Back in the chapter on radical reactions, I pointed out that ethers have a very short shelf life because they're prone to autooxidation. Okay, so that's why we use diethyl ether as a solvent in the lab all the time. We can't store it for long periods of time, so we have to make sure that we buy it relatively fresh and we use it pretty quickly. Right? So watch out for that because the resulting hydroperoxides are very explosive. Okay, so we can this hydrogen that's on that alpha carbon, it's relatively easy to insert an oxygen molecule in between there through a radical mechanism, as we saw back in chapter 11. Okay, so here's a little refresher on that. Okay, so you first start off with the initiation step involves a hydrogen abstraction to create your initial radical. Okay. And then in the propagation step, that radical reacts with an oxygen molecule. That oxygen molecule, or that oxygen then still has a radical left over on it. That will do a hydrogen abstraction on another ether molecule, okay, which is what we saw back in that initiation step. So notice that we get the peroxy product, and we've recreated the initial ether radical, which we see back here. And so the chain reaction continues. All right, so there's the net effect for making a peroxide from your ether. Okay, that's the net reaction. We've just kind of written everything out with RH just to simplify things here. But essentially all we're doing is we're inserting an oxygen molecule in between our carbon and hydrogen bond. Okay, so let's move on to epoxides. So as I pointed out, epoxides are are kind of like ethers, except now the two carbons coming off your oxygen can be connected to each other. All right, so we call these cyclic ethers. All right, now I've kind of fixated on epoxides just because they're going to be very reactive and they're very useful for that. But in that class of system, you don't necessarily have to have the carbons connected directly. You can have cyclic ethers where you have your R groups just connected together by however many atoms. They don't have to be just the two carbons connected directly. Okay, you can have multiple carbons in between. And there are different names for those. So we call the epoxide ones oxirane, and you can increase the number of carbons in your ring and you get different names accordingly. But like I said, the oxirane system or epoxide systems are the ones that are going to be most reactive. All right. The reason for this, as you probably guessed, is the large amount of ring strain you have here. Okay, so we've got this isosceles triangle that we've drawn here. That bond angle is somewhere in the ballpark of, let's say, 60 degrees, or it wants to be 60 degrees. But remember, that's an sp3 carbon. What does that bond angle actually want to be? Right? It wants to be somewhere in that 109 degree ballpark. So 60 degrees to 109 degrees is a significant difference. Okay, so there's a lot of ring strain in that molecule, which allows this to readily react. Okay, so because your carbons in your epoxide have two of their bonds taken up, they have a bond to each other and a bond to that mutual oxygen, that leaves room for only two more alkyl groups, or two more groups in general, because of course you can have hydrogens there, to each carbon, so 4 R groups in total. All right, so of course the simplest epoxide we have here has just all 4 hydrogens substituted, but of course we can have other alkyl groups in there instead of an epoxide. Okay, so let's talk about naming epoxides. There are 2 ways you can go about this, right? You could treat your oxygen as a side group, or you can use your your epoxide, your ring system as the parent name. Okay, so let's look at both ways. So if we're treating oxygen as a side group, you take your longest carbon chain and you list your epoxy group as a substituent. Now, when you're labeling the locants for that substituent, include both the carbons involved, which is a little counterintuitive. Like, we haven't done this for any of the other functional groups that take up more than one carbon, right? So like if you have an alkene or an alkyne, you only list the lower of the two numbers. Whereas here for your epoxy substituent, we're listing both numbers. Okay, so watch out for that. That's one thing that's a little bit different than some of the other examples we've seen with other functional groups. Now, if we use oxirane, right, which remember is the proper name for epoxide, if we use that as our parent name, of course, that goes at the end of the name, and we treat everything else as substituents on that. Now, for assigning locants, the oxygen is given priority. That's the number one position. Okay, the other two carbons are 2 and 3 accordingly. Now, which one's 2 and which one's 3? Depending on the tiebreakers you have, you want to give lower priorities to any groups. If this is, if you have groups missing, you want to have the lowest set of numbers. But ultimately, in this example they've given here, it just comes to alphabetical order. Ethyl comes before methyl, and so that carbon with the ethyl groups is given the lower number. All right. Okay. So, with that being said, try these. Here we've got a couple of practice problems. Go ahead and name these accordingly. Treating the epoxide as a substituent is probably the easier way to treat this, to go about this. In terms of these two molecules, these two examples they've chosen are a little bit complicated because we've got an ether functional group in here as well. And we probably have to reference a stereochemistry here, since each of these is kind of asymmetrical, and so these carbons are chiral. Okay, so that being said, let's start off with those methods. So our parent chain here is a cyclohexane, right? So let's start off with that. So we have a cyclohexane. Okay. And so, our priority here, we've got an epoxy functional group here, and we have an ethoxy functional group, right? Or this is or substituent rather, as not a functional group. This substituent here, basically, when we're trying to pick between these, I think they've got equal priority. So really, I guess we just go off alphabetical order here, and epoxy comes before ethoxy. So we're going to give the lower set of numbers to this. So we'll number these carbons as 1, 2, and 3. So this is 1, 2 epoxy, and 3 ethoxy cyclohexane. Now, of course, I pointed out that we want to have to mention stereochemistry here, since we have we probably use an R or S designation here accordingly. Okay, so if I was looking at this and this hydrogen sticking towards me, if I'm assigning priorities to the groups coming off of this carbon, this oxygen has a higher priority, followed by this carbon with an oxygen connected to it, followed by this carbon with hydrogens and carbons connected to it. So looking at it this way, it seems to go clockwise, but remember, we're looking at this backwards. The hydrogen's pointing towards us instead of away from us. So it's actually counterclockwise if we're looking from the opposite side. So this would be the S, using the Kahn-Ingold-Prelog system. Okay. All right. So with this one here, we've got 1, 2, 3, 4, 5, 6 carbons. So that's our parent chain's hexane. We're kind of treating this kind of rather similarly, though our locants will be a little bit different. It looks like also, since the ethoxy group is closer to this end, I think we'd probably actually start numbering from this end. So it looks like our ethoxy groups at the number 2 position, and this is going to be a 3,4 epoxy. So 3,4 epoxy 2-ethoxy hexane. All right. And of course, we can assign locants to this too, and I think it comes back to the same thing. It's going to be S for the same reasons the other one was. All right. Now, regarding treating our oxirane as our main group, it's going to be a little complicated with since your cyclohexane's kind of part of the ring. It kind of loops in on itself. So I would say that if you were trying to name this, treating the epoxide as a substituent makes more sense than trying to use the other naming system. For this molecule, though, we can totally do that, right? Because you could treat, we've got an ethyl substituent on this carbon, and we have a substituted ethyl on this carbon. So if we were using, our oxirane suffix, okay, and we were numbering this, I would probably give our, just alphabetically, this looks like this is a 1-ethoxy ethyl group as opposed to just an ethyl group. So let's give the lower number to this guy. So that would be 2-ethoxy and 3 1-ethoxy. Oh, whoops, sorry. I just realized this is not an ethoxy group, that's an ethyl group, so sorry. My bad. This is 2-ethyl, 3 1-ethoxy, ethoxy ethyl. Oops. Close parentheses. Oxirane. There we go. So yeah, so that one's a little bit complicated. Sorry for the mess here, and sorry for, looks like my, I'm losing a little bit of resolution on my writing here. But yeah, so this is 2-ethyl, 3 1-ethoxy ethyl oxirane. Okay. We saw back in chapter 9 when we looked at addition reactions across an alkene, we saw that a way to do a dihydroxylation, well, there were two ways to do dihydroxylations, right? You could do a syn dihydroxylation or an anti-dihydroxylation. To do it with a syn addition, you wanted to use an osmium 8 oxide, right? So you'd have your osmium coordinating to two oxygens that would coordinate to your alkene, and that's why it would be the syn addition of those oxygens that would go on to form your two alcohol groups, right? That would make your diol. We saw that, however, we can do the anti-addition by going through an epoxide intermediate if we use a peroxy acid. So I think MCPBA was the common peroxy acid that we used a lot for doing that reaction. Peroxyacetic acid is another example as well of a peroxy acid that we can use to affect this change. All right, so the bottom line is we basically make the epoxide from this. We could then have a nucleophilic attack on that epoxide with a hydroxide ion, for example, and that would cause the diol to form. So let's look at the stereospecificity of this problem, right? So notice that since the oxygen kind of sits on top or comes out the bottom of this alkene accordingly, any substituents that are on your alkene are still in the same order. So if we have a cis alkene, those substituents will still be cis in our resulting epoxide. Okay, and vice versa. Here we have trans alkene. Notice that those two alkyl groups are still trans to each other. Okay, so that being said, another way to make an epoxide from something we've seen back in chapter 9 is the halohydrin reaction. Okay, so we saw how to do the halohydrin reaction, right? We would take an alkene, react it with bromine, but using water as a solvent instead of, like, let's say, carbon tetrachloride. And we would wind up doing an anti-addition of bromine and an alcohol group, right? Our our bromine would take up one side of the alkene when it forms a bromonium ion, and so our alcohol group would have to, attach, our water nucleophile would have to attack the opposite side, and that's why these two are trans to each other. Okay, this product of our halohydrin reaction, okay, called a halohydrin, can then be converted into an epoxide through a ring closing reaction. Okay, so we'd use sodium hydroxide to affect this change. Let's see how that works. Okay, so your hydroxide starts off by doing a proton transfer. It plucks off a proton from your alcohol group, okay, which remember is very mildly acidic. So it converts this into a corresponding alkoxide. And remember, that alkoxide now is nucleophilic. We have a bromine. That's a great leaving group. That's just one carbon away. So that nucleophile attacks that alpha carbon next to your bromine and kicks off that bromine. And that's how it forms the corresponding epoxide, right? So it just does a regular SN2 reaction, but it does it intramolecularly. So your nucleophile and your leaving group are both on the same molecule. Okay, so so that's basically two ways we could get we can make an epoxide starting with an alkene. We could do a cis we could use a peroxy acid, but instead of going on to forming the diol, we could just stop at the epoxide there. Or, as I mentioned, we could do a halohydrin reaction using bromine and water, and then add sodium hydroxide to convert it into the epoxide, as we just saw. Okay. Now, all of the epoxidation methods we've looked at so far have not taken into account enantioselectivity. All right, there weren't any chiral centers we had to really worry about. Okay, so if let's kind of illustrate this. So look at this alkene over here and ask yourself, what are the products going to look like? Okay, well, if we add our epoxide in the top here, I mean, the key thing is we've got these methyl groups that are trans to each other, and they'll still be trans, but you've got to realize that when we add our epoxide, we're going to turn this carbon and this carbon into chiral centers, right? This carbon over here is going to be attached to the oxygen of your epoxide. It's going to be attached to this carbon here. It's going to be attached to a methyl group, and it's going to be attached to an isopropyl group. Okay. Likewise, this carbon is attached to an ethyl group, a methyl group, the oxygen, and this carbon. Okay, and please note that this half of the molecule is different from this half of the molecule due to this ethyl group and this isopropyl group. So it's not like you have any cancellation out that way, right? There's no like additional symmetry, rotational or otherwise, or mirror planes. Okay, actually, I guess when it comes to enantioselectivity, the mirror plane is what's important, because then you have a meso compound. Okay, but anyway, my point here is that depending on whether you form your epoxide pointing up or pointing down, you will have inverted the chiral centers accordingly. And since there's nothing that controls what side the epoxide adds on, you're going to get a mixture of both enantiomers. You're going to get a racemic mixture. Okay, and this is true for whichever method you use. I've been talking mostly about using a peroxy acid, but the same would happen with our bromine, with our halohydrin, right? Depending on which side your bromine adds on, okay, to form that bromonium, that can form either enantiomer, okay? And so you'll get a racemic mixture eventually the same way. So here are the two products if you want to see what that looks like. Okay, so you could have that epoxide pointing upwards or downwards, and notice that your chiral centers are both inverted accordingly. So how do we get one specific enantiomer, or how do we be enantioselective when we're trying to, when we have like multiple enantiomeric products we could make, right? When we could get a racemic mixture. To do this, we want to use a catalyst. So the Sharpless catalyst, named after Barry Sharpless, I randomly ran into him in a bar once, and I've got anecdotes from that meeting, but so if you're ever bored, I'm sure I could tell you those. But I'm going off on a tangent now. Let's get back to get away from stories that start with a Nobel laureate walks into a bar. with the sharpless catalyst, we have a titanium complex here. We've got a titanium tetraisopropoxide, and we reacted with, this is actually the pre-catalyst. So we pair it up with DET, and depending on the enantiomer we select of the DET molecule, we can cause an allelic alcohol such as this to be converted into a specific epoxide. So with the alkene in our alcohol, we can add an epoxide here, but we can add it either above or below this double bond depending on the DET version that we select. All right, so that's where so again, like this, depending on how your DET, depending on the enantiomer of DET you select, it pairs up or coordinates to that titanium in a particular orientation, and that then causes the oxygen to add on to our alkene accordingly, on one direction versus another. Okay, so let's look at some ring opening reactions of epoxides. Now, these are very, very common, very, very useful. As I pointed out, one of the reasons why epoxides are so reactive is because you've got so much ring strain on that three-membered ring. So it makes sense that ring opening reactions make up a bulk of very easy, useful reactions you can do with epoxides. In fact, you've already seen them in the case of doing the anti-dihydroxylation addition reaction back in our chapter on alkenes, right? We saw that when we treat a alkene with a peroxy acid like MCPPA, you'll get the epoxide, but more importantly, we'll go on to get the corresponding diol. Okay, so anyway, let's look at some other ways we can react our epoxides. So typically, you want a nucleophile to attack that one of your two carbons, right? Your nucleophile attacks your carbon, and it causes that bond to the oxygen to break, forming the corresponding oxide, which can then do a proton transfer and go to form an alcohol group. This is what happens when we did our anti-dihydroxylation, right, with our alkenes. We already saw this in another chapter. Okay, but again, that's one. Depending on the type of nucleophile you use, you can get different types of products. So we've seen that alkoxides are leaving groups. They're not super great leaving groups. We can make them better by protonating that oxygen and having it leave as an alcohol. But this is where that ring strain comes in. I mentioned earlier that it's really useful that an epoxide has such a strong ring strain, because that really makes the epoxide more reactive. As we can see here, those epoxides are very unstable, and they start off at a higher potential energy, but then the benefit there is that you have a much lower activation energy required, okay, as opposed to using a much more stable ether as your reactant. All right, so with I mentioned that we can use other nucleophiles besides just hydroxide, and so here you can see multiple types of nucleophiles we could use. And again, we're using metal salts or ionic compounds, so we're getting the anion version of these nucleophiles. So, for example, here we have sodium alkoxide of some sort. So we have an alkoxide nucleophile, and we can add an alkoxy group there. So we can make something that has an ether functional group and has that alcohol. All right. We could use a cyanide ion as our nucleophile. Interesting thing here, notice that we've got a carbon. We're essentially extending that carbon skeleton there. Something to keep in mind for future reactions and for adding to that to our synthetic toolkit. We could use a thiol or sodium hydrogen sulfide. Sorry, not a thiol. We'll get into thiols in a little bit, but for this to be a thiol, that needs to be an alkyl group. So sodium hydrogen sulfide is a nucleophile as well. Here we have a Grignard reagent. I think we ended the last chapter with an example of this, actually, and I pointed out that that was kind of atypical of some of the examples we saw in that chapter, because mostly we saw Grignard reagents having that carb anion from your Grignard reagent as a nucleophile. and it would attack a carbonyl of some sort and convert it into an alcohol, right? But I think we ended that chapter, we did a practice problem where instead of having the alcohol group on the carbon that your grignard was attacking, it was one carbon away. And so the reason for this was because it was actually an epoxide that we used. We had the Grignard reagent react with the epoxide. Notice now we have an alcohol group coming off one carbon away from the carbon that the Grignard attacked. Okay, so something to keep in mind. Okay, and of course you can use a hydride. So lithium aluminium hydride, for example, is a source of hydride. Hydride's nucleophilic enough to easily break up that epoxide ring, and you can just essentially just add a hydrogen there. That's just a regular alkyl group, and you've turned this into a regular alcohol now. So with that in mind, let's pay attention to the regio and stereoselectivity of these nucleophilic attacks. So we have a nucleophile coming in, so you'd expect a regular SN2 mechanism, and you'd expect it then to follow the patterns we saw with SN2 mechanisms. You typically have your nucleophile preferring a less hindered site, so a primary site is much more preferential to a tertiary site. Okay, so with that in mind, let's keep on looking at what we actually do observe. All right, so first of all, let's look at the generic reaction. Right, we have under acidic conditions, we've seen that we can protonate our oxygen, have our nucleophile come in and attack one of the carbons. In this case, it's a symmetrical epoxide, so we don't have to worry about regio or stereo chemistry just yet. And that ring opens up, right? So with that in mind, as long as we have acidic conditions and we make, we have our, we make that epoxide even more ready to open up. Even a weak nucleophile like water and alcohol can be used as our nucleophile. This top reaction is actually how they make antifreeze, which is ethylene glycol, or using the IUPAC name ethane diol. So if I were to just sketch these two products here, when you open this up, this oxygen, of course, will go on to form the to form an alcohol group. So depending on your nucleophile, well, here we're going to add an OH group to this. So basically, you have an OH there, OH there. So this is antifreeze. This is ethylene glycol. Okay. If you use an alcohol instead, you'd still have your epoxide oxygen forming that alcohol group. This would just be an alkoxy group. So this is the product you'd form accordingly. All right. So if you want the full mechanism, here we have that. So you can protonate that oxygen to make this more prone to open up this epoxide. Your weak nucleophile comes in, attacks either carbon. In this case, it doesn't really matter because this is symmetrical. And then with that opens up your ring and forms this alcohol group. You of course now need to deprotonate this to make the stable product we see. Okay, and over here you can see that with where we started off, where we're using water as our nucleophile, and that's where we're getting our ethylene glycol product. So that being said, if we have an asymmetrical epoxide, what regiochemistry preferences do we see? Does our nucleophile attack a primary site versus a secondary site versus a tertiary site? Now, with the nucleophile attacking, right, which we typically see in an SN2 mechanism, if you recall, a SN2 mechanism prefers a primary substrate versus a tertiary substrate. This is a sterics thing, right? Our nucleophile likes easy access to that alpha carbon. If you have too many bulky groups in the way, it's not going to have that step occur very easily. And remember, that's the only step in an SN2 mechanism. All right, and we actually see that here in this example here with the primary versus secondary site. Clearly, there's a preference for that primary site. But here's what's really weird. If we have a tertiary site available, now normally under SN2 conditions, you don't see a reaction there, but instead we do. We see a preference for that product. Now, this mimics what we see with SN1 mechanisms, right? We prefer making, this will go through a carbocation intermediate, and that carbocation is stabilized. Okay, there's an electronic effect there, an induction effect from the alkyl groups, right? It stabilizes the positive charge on our carbocation, giving it more time to react and form product. Right. So what's going on here? To understand this better, let's look at some of the stereochemistry involved. You know, remember with an SN2 mechanism, you have an inversion of product, right? Because your nucleophile comes in, does a backside attack, and it forces any other substituents to go in the opposite direction. All right, so you can see here, your nucleophile comes in, attacks this site over here, and we still do see an inversion. If this were an SN1 mechanism, we would see a racemic mixture of products because your carbocation would be flat, and your nucleophile could attack either side of it, right? So that's something to keep in mind, that this is still an SN2 mechanism, but what must be going on is that there's some partial carbocation character. There's a little bit of SN1 to this SN2 mechanism. All right, we kind of saw this back in some of the addition reactions, some of the intermediates with additions to an alkene. So, for example, when you form a bromonium ion, or in a mercuration-demercuration, that mercuration step with a coordination to the mercury center, we had this sort of partial positive charge on the site that our nucleophile is going to attack. And so having those alkyl groups nearby helps stabilize this transition state. Okay, so that's something to keep in mind, right? So if you look at this example over here, now here we have a tertiary site over here, and notice that we have an inversion of stereochemistry. This alcohol group's adding onto that carbon, and that methyl group that was pointing away is now pointing towards us here. Okay, and this oxygen from our epoxide is becoming this alcohol group here. Okay, so to do this reaction under acidic conditions, you probably just have an acid and water, I think, would carry this out, since we're adding just a regular alcohol group as the group coming in. So you could have just added that with water as your weak nucleophile. Okay, and so that's it for epoxides. Let's move on to thiols and sulfides. Now, sulfur is in the same group of your periodic table as oxygen, right? So that's why we have a lot of analogs here between our our oxygen-containing organic compounds, like our alcohols and our ethers, and that's why we have just sulfur versions of those, namely thiols and sulfides. Okay, so in the case of a thiol, as I pointed out, it's pretty much just like an alcohol, except instead of an OH group, you have an SH group. The naming is also very similar. Instead of dropping the E in your parent chain name and replacing it with "ol," you leave the E in there and you just add the suffix thiol to that. Okay, so here you can see what would be a butanol becomes butane thiol. Okay, now in the case of thiols as a suffix, well, that would be just you would just end with thiol, right? But we've seen that with a lot of functional groups, they can sometimes be substituents if you have a higher priority functional group, right? So for example, an alcohol group can be called, when it's treated as a substituent, could be called hydroxy, for example, right? We've seen it in this chapter with epoxy versus oxirane, right? Well, in the case of thiols, their prefix name, when you're treating a thiol as a substituent and not the main group, is a mercaptan. So the prefix we use is mercapto. Thiols actually have a lower priority than alcohol. So you can see here in this molecule we have a thiol group and an alcohol group. So the name ends with butanol, right? We have 1, 2, 3, 4 carbons, and so there's 4 carbons, and that alcohol group is given the lowest, the lowest number because it has the main priority. So it's 1 butanol, and we have a methyl group and our thiol group on the number 3 carbon of our 1 butanol. So it becomes 3 mercapto, 3 methyl, 1 butanol. Again, we're going off alphabetical order here. Okay. All right. So yeah, basically, if you're wondering about that name, because you may have like also just colloquially heard that name, refer if you've ever heard of thiols or this class of compounds. Yeah, you might sometimes hear that name quite a bit and just hear them collectively known as mercaptans. The name comes from the ability of these thiols to form complexes with mercury. Okay, now what are thiols really known for? And mostly they're known for smelling bad. So hydrogen sulfide itself smells of rotten eggs. It smells of brimstone. It's the other term you've heard to describe it. So things like volcanoes and stuff give off a lot of these give off hydrogen sulfide and a lot of these thiols and other compounds and other sulfides, and that's what gives them that distinct smell. But thiols in general have a lot of really unpleasant odors. All right, so skunk odor, for example, is made those compounds are thiols. In the case of when you hear beer going skunky, that's because a lot of the compounds in the beer have reacted with light to make these really stinky compounds. Okay, that remind people of skunk odor. All right, that's why, by the way, that beer is usually bottled in brown bottles. It's to prevent light doing those reactions. Okay. Now, it just turns out that we've just evolved to be very hypersensitive to these thiol smells. There's a reason that we have typically a very sort of repulsive reaction to it. And we take advantage of that. So natural gas and other alkanes actually don't smell of anything. So what happens is we add tiny amounts of methane thiol to natural gas to give it a smell. This is very important because if you have a gas leak, you want to be able to detect that there's a gas leak, and being able to smell any leaked gas is very, very important. Okay. So so we've seen hydrogen sulfide, the hydrosulfide ion from thiol is a very strong nucleophile. We've seen that already. So we've seen SN2 reactions that entail using that as our nucleophile. And this is a quick and easy way to make a thiol. Right? You can take an alkyl halide, react it with sodium hydrogen sulfide, and basically make the corresponding thiol. Okay, so it again depends on the so you have a kind of a preference for due to that strong nucleophile, you have a preference for that substitution product. Okay, so it's going to undergo an SN2 mechanism. So please note for this one, you're probably going to get the inversion product accordingly. So your thiol here will have a dash wedge connecting it. Okay, when it replaces that bromine, when it substitutes that bromine. Okay, same thing here. Here, stereochemistry isn't really important because you've got two hydrogens here. This is not chiral. But yeah, so your bromine would replace your thiol, and you'd get propane thiol as your product. And so there's your corresponding products accordingly. All right, let's talk a little bit about the acidity of these. We talked about the acidity of alcohols in the previous chapter. So thiols, of course, also have are relatively acidic. Now, if you remember, thinking back to Ario, those large squishy sulfurs are really good at stabilizing negative charges and forming conjugate bases. So it makes sense that thiols have lower pKa's compared to water and alcohols. All right, so you can see here, if we dissolve a thiol in water, there would be a preference for the thiolate ion, sorry, not in water. If you dissolve it in hydroxide, you'll see that there's a preference for the thiolate ion, right? So that's again because your thiol is a much better acid than the water is in the reverse reaction. So this forward reaction predominates. All right, just like hydrogen sulfide ions, a thiolate ion with that negative formal charge on your sulfur is a great nucleophile, right? It's going to undergo, carry out a nucleophilic attack pretty readily. So if you take a thiol, react it with sodium hydroxide, you can make the corresponding sodium thiolate salt, and you have that nucleophile ready to go. Okay, sorry, that looks like there's a glitch in here in this slide from the publishers, but but just imagine this at symbol is actually a negative charge, and the exclamation point there is a positive charge. Okay, so your sulfide ion is a nucleophile here, kicks off your bromide leaving group, and of course then this can have another thiolate ion act as a nucleophile to that sulfur, kicking off your bromide leaving group back again. Okay, so this bromide that was attacked first becomes a leaving group in the next step, essentially. All right, and notice that when this happens, we formed a sulfur-sulfur bond, also known as a disulfide bridge. All right, so effectively, what's going on here? If you have a thiol and you react in the presence of sodium hydroxide and bromine, you will effectively make a disulfide. Pay attention to the change in oxidation state here. Your sulfur is losing out on a bond to hydrogen, which is less electronegative to it, and it's forming a bond to another sulfur, which is equal in electronegativity to it. Okay, so effectively, your sulfur's oxidation number is increasing as it goes out here. It's getting less negative or more positive, and therefore it's being oxidized when you form a disulfide bridge. Okay, so accordingly, you can do the reverse reaction, or a reduction, and you can do this reduction using hydrochloric acid and zinc. Okay, so you can do that reduction and convert back to the original thiols. So this can also happen through a free radical mechanism, so keep that in mind. That's also a possibility as well. Okay, the bond dissociation energy for a sulfur bond is relatively low. It's 53 kilocalories per mole, which makes sense. Sulfur is a relatively large atom, especially compared to something like a carbon or an oxygen. So it makes sense that this bond is a little bit longer and weaker. Okay, we can, as I mentioned, just as thiols are analogs of alcohols, we can make analogs of ethers called sulfides, also known as thioethers. All right, with the common names of these thioethers, you can just swap out the word ether for sulfide. And if you want to use a sulfide as a substituent, just as if you have like an alkoxy group here as a substituent, so instead of using that oxy suffix to your substituent, we would use thio as the suffix there. Okay, so based on the alkyl group on your sulfur, just use that prefix and add thio to the end, just as the way we add oxy as the at the end of our alkyl name, our alkyl prefix for our alkoxy group. Okay, so to make a sulfide, we're kind of doing a, we again take advantage of thiolates as good nucleophiles, and we just take our thiolate and react it with an alkyl halide. Of course, that's a great way to add on that alkyl group there and kick off your halide as your leaving group, and there's your thioether, your sulfide. All right. Now, sulfides are useful for a bunch of reactions. We've seen that they are kind of, again, you've got that large squishy sulfur that's kind of nucleophilic. So you can have a sulfide do a nucleophilic attack on an alkyl halide, again, kicking off that good halide leaving group. But again, now you've got a positive charge in that sulfur, so something's got to give, right? So you can have another nucleophile come in and pluck off that alkyl group and reform your original sulfide. Okay, so essentially it allows you to transfer this alkyl group from your alkyl halide to a whole bunch of other nucleophiles. Okay, other things you can do with sulfides, you can oxidize them. Okay, you can take a sulfide, you can oxidize it to a sulfoxide, which is kind of like, it's like an analog of a carbonyl compound, except you've got a sulfur instead of a carbon there. And then you can oxidize this onto a sulfone. Okay, so a sulfone is kind of similar to sulfuric acid, except you've got alkyl groups instead of OH groups. All right, so a good so the way you want to make a sulfoxide is you would use sodium periodate to produce your corresponding. You just use that as your reactant to sort of oxidize your sulfur into the corresponding sulfoxide. Okay. If you want to make a sulfone, you would use hydrogen peroxide as your oxidizing agent. So that would take your sulfide and oxidize it straight to a sulfone. So probably going through a sulfoxide intermediate, but it doesn't stop there. Okay. So in the case of sulfoxides and sulfones, while we draw their Lewis structure with double bonds, there's actually very little double bond character. That resonance structure over here kind of predominates quite a bit. Now you're probably wondering about that, because normally you'd say, oh, well, this resonance contributor that's neutral should be the better one, right? We don't have anything going under the octet rule, and that's usually great. Why is the one with formal charges all of a sudden the better resonance contributor? The reason for this has to do with the octet rule. Now, normally we say that if something goes under the octet rule, that makes it a less stable contributor. Sulfur, being the large squishy atom it is, and with access to those d orbitals, can actually go over the octet rule, but that doesn't necessarily mean that's a great thing for it, right? So notice that here we actually exceed the octet rule in the neutral contributor, whereas here we are within the octet rule, right? We've got 2, 4, 6, 8 electrons around that sulfur meeting the octet rule. Same thing here. This sulfur has 2, 4, 6, 8 electrons around it, as opposed to 2, 4, 6, 8, 10, 12 electrons around it. Okay, so that's, in case you're wondering, why is this why do the sulfoxides and sulfones have so little double bond character? Why isn't that neutral resonance structure the more stable one? That's the reason. All right, so in the case of sulfides being so readily oxidizable, that makes them really great reducing agents, right? Because they themselves can get oxidized so easily, they will reduce other things quite readily. All right, so if you recall back when we did ozonolysis reactions, we had dimethyl sulfide, or DMS, as the other reagent in there along with ozone. Okay, so what's the reason for that? Well, the reason is that the ozone only makes this intermediate. You need the dimethyl sulfide to do the actual cleavage of this molecule to make the 2-carbonyl products that we see. All right. So if you recall the overall reaction, your alkene reacts with ozone and DMS, and it just you just split that alkene down the middle, and you basically turn each of these carbons into carbonyls. Okay, so you just sort of insert oxygens there. Right. If you're curious about what happens to the DMS, you lose it as DMSO, or dimethyl sulfoxide, which, if you recall, it's a really good polar solvent. All right. So with that in mind, let's try a practice problem out here. So have a look at the starting thiol here. Look at the reagents we use, ask yourself what product it makes, and then ask yourself how you can make this corresponding product. What reagents would you use here accordingly? Okay, so if you pause this and rejoin us now after trying this out, you can see that we've got a thiol here, and we're reacting with sodium hydroxide, which just deprotonates that and makes the corresponding thiolate, which is, again, good nucleophile. And this reacts then with this alkyl halide and does an SN2 reaction, an SN2 substitution. So we have this alkyl part of our alkyl halide that remains behind, and our thiolate does a backside attack, right? It inverts the stereochemistry here because it's an SN2 substitution. So instead of having a solid wedge, our sulfur is connected with a dashed wedge. Okay, that's kind of what we're seeing over here in the final product. And of course, this thiol has this alkyl group attached to it, so it looks kind of like this. Okay, and again, we see that in the final product as well. The only difference, of course, is this is a sulfide. And here we've got to convert it to a sulfoxide. Now remember, to do that, we need the sodium periodate. That would be our sodium metaperiodate would be our our reagent here. Okay. All right, so with all that being said, let's look at some of the synthetic strategies we'd use all of these new functional groups for. All right, so we've seen that unlike, and this again is coming back to that last question of the previous chapter, right? I pointed out that unlike using a Grignard reagent with a carbonyl, where the alcohol group and the alkyl group from your carbanion are attached to the same carbon, with an epoxide, the cool thing is that you can have them on adjacent carbons, right? So that's essentially what's going on when you have a nucleophilic attack on your epoxide. You're installing some functional group and an alcohol group on adjacent carbons, not the same one. Okay, so have a look here. Try this problem out. Okay, if you want to do a retrosynthesis on this, a retrosynthetic analysis, notice that we have a nitrile group here and an alcohol group here, and they're an adjacent carbon. So you can kind of figure out the penultimate step probably involved some epoxide where this oxygen was connected to this carbon, and you had sodium cyanide provide that cyanide nucleophile to add on this nitrile group here. So of course, if you're going retrosynthetically from there, and you've got an epoxide, right? How do we get the epoxide from this starting alkene, right? And clearly you can tell this is the same alkene. We're starting with the same positions. There's that methyl group that's over here, and that's a good frame of reference. This is where that alkene used to be. So we got an epoxide that was over here, right? So basically our intermediate kind of looks like this. So we're going to this intermediate here. There's our methyl group. This epoxide is our intermediate that we can then use to produce this. Okay, so this is done easily enough with sodium cyanide, of course. So think about how you would want to add a epoxide to an alkene like this, right? So you could just use something like MCPBA to do this, and that's how you could work through that. I've already mentioned to you in the last chapter about how Grignard reagents are really useful for extending your carbon skeleton, because of course your Grignard consists of a carbanion that you're using as your nucleophile, and those carbons extend your carbon skeleton. If you're using an epoxide as your electrophile here, you have to take into account that you're extending by another 2 carbons. You're extending the carbon skeleton of your Grignard by 2 carbons, right? So instead of thinking of it as your Grignard as what's extending the carbon skeleton of these 2 carbons as your parent chain, we could also think of it backwards. We could think of the epoxide as the starting material, and the Grignard is what's attacking that and extending that carbon skeleton, or vice versa. So those are multiple ways to try and sometimes see your reagent and see your product and kind of wrap your head around the problem, right? If you're trying to add on 2 carbons, it might be helpful to think of your epoxide as the reagent. If you're thinking about starting off with your epoxide and extending the carbon skeleton, it might be useful to think of the Grignard as your reagent acting on that. Okay, but the bottom line is that we're getting an alcohol with 2 extra carbons compared to our Grignard. Okay, so basically we can, I guess the key thing there is to watch out for the extra 2 carbons from our epoxide. Please note the difference from this in the last chapter, where we had our carbanion from our Grignard directly attacking a carbonyl carbon, and therefore it's that same carbon that your alcohol group's attached to, right? It's that alpha carbon, whereas here it's on the beta carbon, right? Your alpha carbon connected to your alcohol group is 1 carbon away from the carbon that your Grignard carbanion attacks. Okay, so with that in mind, let's try this problem out. Okay, so this is actually kind of similar to that last problem in the last chapter in our additional practice problems in the previous chapter. So feel free to pause this video and try this out. Okay, so by similar to, I meant exactly identical to. So if you want to check your work, you can definitely just look at that last slide of the previous chapter. But just to jog your memories, we have an alkyl halide here. You can convert this into a Grignard by reacting this with magnesium and ether. And so you're just inserting a magnesium in here between the carbon and the chlorine. We can then react that with an epoxide that has this isopropyl group coming off one of the carbons. All right, so that's basically this. You initially had this oxygen and these two carbons connected to each other in your epoxide, and that's what your Grignard's attacking, and that's why you're forming this carbon-carbon bond here. Okay, and that resulting nucleophilic attack opens up your epoxide and creates this alcohol group here that's two carbons away from where your carb anion used to be. All right, and that's it for this chapter. So let's work through these practice problems, and yeah, and then we'll go from there. But that's actually it for this semester. So let's take a second, name name this molecule here, and then try drawing out this ether over here. Okay, so please note that it's probably a little bit easier to treat this this cyclopentyl group here as your parent chain and go from there. Likewise, when you're trying to draw this one down here, it looks like here we've got the common name. Notice that we're ending with ether as opposed to a alkane suffix. So that tells you that we've got two alkyl groups here that are attached to our oxygen. One of them is clearly a phenyl group. That's a benzene ring. And you can figure out what the other one is here. It looks like it's a cyclohexyl with a substituent on that cyclohexyl. All right, so feel free to pause this and go ahead and try this out. Okay, so here are your answers if you want to check them out. So here we have cyclopentanol as our as kind of our root there with an alkoxy group attached here. It's a tert-butoxy group, right? We have a tert-butyl on our oxygen. The alcohol is the primary group. That's why we have the name pentanol on this, cyclopentanol. So that alcohol group's at the 1 position, which makes this 1 kind of redundant. If you wrote this without putting that 1 over there, that's fine. You could have just written this as 2 tert-butoxy cyclopentanol, and that would still be correct. Notice that we have chiral centers here, so we do need to put designations, RNS designations for those chiral centers as well, so don't forget that. Okay, for this one here, of course, this is what that looks like. So here we have a cyclohexyl group, and that oxygen is attached to the 1 position, so this methyl group's at the 4 position over here. All right, so here's a synthetic problem. Looks like we have both reactants and intermediates and reagents missing. So take a second and try this out. Okay, so notice that here we've got an alcohol, and you can see the reagents here imply a hydroboration, hydroboration-oxidation reaction. So remember that's an anti-Markovnikov addition across an alkene. Okay, so think about what the alkene would have looked like. Okay, so that OH group would be missing, and there would have been a double bond either here or here. Okay, so which one would be the anti-Markovnikov addition accordingly? Okay. So then, of course, here we have a oxidizing agent here, that's chromic acid. So ask yourself, what would this secondary alcohol get oxidized to? Okay. Now, here we've got a lot of stuff missing, so you might want to work backwards. You want to do a retrosynthetic analysis from this guy and work your way back. Okay, so look at all of these pieces and ask yourself, which ones came from this? Well, I'm guessing it's probably this carbon skeleton here. So, and here's that, this oxygen is probably this oxygen here. So ask yourself, how did we convert that into an ether? Okay, that was probably involved in the intermediate somewhere. Okay. Also, notice that we've extended the carbon skeleton here. So by that fact alone, that might give you a hint as to what we were doing. Okay. All right, so there we go. So note that we had an alcohol group here, and that became a ketone over here. You could then use a Grignard reagent to extend the carbon skeleton, as we've seen here. Okay, now doing so converts that that ketone into an alcohol, which you can then convert into an ether using sodium hydride and an alkyl halide. All right, let's try another problem like that. So here we have an epoxide, and it looks like we made it by using MCPBA. So ask yourself, well, what does MCPBA react with to make an epoxide? Well, again, it's an addition reaction, right? So ask yourself, what did the alkene look like? And I think that one should be pretty straightforward. Okay, so here that epoxide opens up to make this alcohol. So think about what you'd use to do that. Think about how else this molecule has changed. So what did you add on to this epoxide? What did you use as your nucleophile to get this specific alcohol? Okay, and then ask yourself how, what will this become if it reacts with hydrochloric acid? Likewise here with this epoxide, we want to open up this epoxide and make this product. So ask yourself, what nucleophile did we use over here? Okay, so that should put in the answers there accordingly. All right, so this one here involves a multi-step synthesis. Notice that we're changing functional groups and we're extending the carbon skeleton. So take a second, pause this, and try this one out. All right, so this one involves lots of steps. So we're starting off with an alcohol. See, we react this with phosphorus tribromide, and that basically swaps out your alcohol for a bromine, right? We saw that in the last chapter. We can convert that into a Grignard reagent using magnesium and ether, and then so essentially we're just we're turning this part here into a carbanion. Okay, so you can see that here in our final product. So we've kind of attached it to this half of the molecule. Okay, now there are multiple ways to go about making this. This is just one synthesis, right? I think I'll have an alternative on the next slide. But basically, you could have this attack your ketone here, convert that into an alcohol, which you can then tosylate to make it a better leaving group, make an alkene. You're going to make the Hoffman product, so that puts a double bond over here, and then using MCPBA, you can turn that into an epoxide. Okay. Alternatively, we could start off with our Grignard with an alkene already built into it, and then use MCPBA to convert that into an epoxide more directly. Okay, so that's another option there as well. And that's it for this chapter, which means that's it for this semester. So all you've got left right now is your final. So be sure to check out the practice exams that I've put on Blackboard. They're old ACS exams. Those questions are from old ACS exams. I can't give you anything too recent due to the fact that ACS, just for test security reasons, they might reuse questions or you reuse parts of questions, and so I have to use old decommissioned exams for your practice. So take those exams with a pinch of salt there, because curriculum changes, sometimes language changes a little bit in the way they phrase questions, but for the most part, they'll give you a feel for how the ACS likes to ask its questions. Secondly, please note about these practice exams, they are full 2-semester exams. They're the type of practice exams, the type of exams you would have taken after taking Chem 204. So actually when you do take Chem 204, you'll see the same practice exams again next semester, but you'll understand more of it. The reason I'm telling you this is that when you are taking the practice exams, realize that not all the information on there is going to be on your exam. All right, some of those are second semester topics, and in fact, a good chunk of those are second semester topics. So my advice is have the study guide in front of you as you prepare for the final, and if you come across a question that doesn't seem familiar, and you check the study guide and you say, oh, this is not a topic that's covered for this semester, I would, just skip that question. And as always, feel free to ask me questions. That's typically how I run my reviews for my exams. It's I have students go through the study guide and say like, oh, it's been a while since we've done this topic. Can we do a practice problem on this? Or they're doing the practice file and they're like, oh yeah, I got this question. I'm not sure how they got the answer here. Pretty much all my reviews for any final are very student directed. So, my advice is go through those practice exams, go through the study guide, and then let me know if you need help getting ready for the final. Okay. That being said, thanks for a lovely semester, both lecture and lab. And good luck with your final. Have a very good, restful break. And I look forward to seeing you next semester. You've probably noticed me allude to a lot of the topics in next semester, in this semester. Like I'll often say like, oh, this, okay, understand that this is how this is good enough to understand how this works now, but you'll really understand how this works next semester. So we'll go into much more detail on some of the things that we've glossed over a little bit in this semester. So hopefully next semester will be pretty fun and interesting for you guys. And but yeah, then enjoy this time off once you're done with your final. Good luck, enjoy your holidays, and look forward to seeing you guys next semester. Take care.